us to truly consider what causes objects around us to move, or, for that matter, why they eventually come to a stop. This fundamental puzzle, well, it baffled even the greatest minds for centuries. Today, we're taking a deep dive into these very mysteries, concepts that are not just fundamental to understanding our physical world, but absolutely crucial for your upcoming exams. We're talking class 9th, 10th, 11th, 12th boards, and competitive exams like UPSC, SSC, state PSCs, CDS, CAPF. Our mission is simple: equip you with a rock-solid understanding of force and the laws of motion. We'll draw out the core concepts and practical applications directly from our source material, making sure you're fully prepared.
It's interesting. For a very long time, the prevailing belief was quite different. People thought rest was an object's natural state. The common idea was if you wanted something to move, you had to continuously push or pull it, keep applying effort. But this perspective, it underwent a dramatic revolution. Thanks really to the pioneering insights of Galilei and then Sir Isaac Newton. They laid the groundwork for our modern understanding of dynamics, how things move.
And how do we define this force in physics terms? We feel pushes and pulls, but what is it?
Right. In daily life, we experience force as a push, a hit, or a pull, often a muscular effort, But while we can't literally see or taste force itself, we always observe and feel its effects. And these effects are precisely what define a force in physics. Things like starting a stationary object pushing a trolley, for example, or stopping a moving one, like catching a ball. It can also change an object's speed, its direction, or even its shape and size. Think about pulling open a drawer, or a hockey stick striking a ball, changing its path instantly, or even stretching a spring, or squeezing a rubber ball so it deforms. Force is the unseen agent behind all these visible changes.
The unseen agent, I like that. So if force is defined by its effects, how do we start distinguishing between forces that actually cause motion versus those that don't? What's the key distinction there for our understanding?
That's a crucial distinction. We differentiate between what we call balanced and unbalanced forces. Now, balanced forces occur when multiple forces act on an object, but their net effect, the resultant, is zero. Imagine, say, a wooden block on a table. If you pull it from both sides with exactly equal force, what happens?
It stays put.
Exactly. It remains stationary. Balanced forces do not change an object's state of rest or its state of uniform motion. But if those forces are unequal, if one pull is stronger than the other,
then it'll move towards the stronger pull.
Precisely. The block moves in the direction of the greater force. This is an unbalanced force. And here's the critical point for your exams. It is the unbalanced force that is the sole cause of any change in an object's state of motion. Whether it starts moving from rest, speeds up, slows down, or changes direction, an unbalanced force is responsible.
Okay, so an unbalanced force is the trigger for change. Now, where does friction fit into this picture? We encounter it all the time.
Friction is absolutely crucial, yes. It's a force that always opposes motion or the tendency of motion. Consider children trying to push a heavy box across a rough floor. Initially, they might push, but the box doesn't budge. Why?
Because friction is pushing back equally hard.
Exactly. The force of friction between the box and the floor is balancing their push. It's a balanced force situation initially. Only when their pushing force exceeds that maximum static friction does an unbalanced force emerge, and then the box starts to move. Think about riding a bicycle, too. When you stop pedaling, you don't keep going forever at the same speed.
You slow down and stop eventually.
Right, because of friction from the road and air resistance. These opposing forces create an unbalanced force that slows you down. So this illustrates a fundamental principle. To accelerate an object, that means to change its velocity, an unbalanced force is always required. However, and this is important, for an object to maintain a uniform velocity constant speed in a straight line, the net force acting on it must be zero. The forces must be balanced.
That idea that uniform motion doesn't need a continuous push feels counterintuitive based on everyday experience with friction. This leads us straight to Galileo's work and Newton's first law. How did Galileo's experiments challenge the old thinking?
Galileo's experiments with inclined planes were truly pivotal. They directly challenged those long-held ideas. He observed simple things first. A marble rolling down an incline, its velocity increases. Rolling up an incline, its velocity decreases. Obvious enough. But then came the genius part. He imagined an ideal situation, a perfectly frictionless, double-inclined plane. He reasoned, if a marble rolled down one side, it would roll up the other side to reach exactly the same height it started from.
Okay, assuming no energy loss.
Exactly, in an ideal, fictionless world. Now, what if he made the second plane, the receiving plane, perfectly horizontal? What would happen then?
Well, if it's trying to reach the same height and the plane is horizontal, it would just keep going.
Precisely. Galileo deduced that in this ideal scenario, with no opposing force like friction, the marble would continue to travel indefinitely in a straight line at a constant speed. It's always striving to reach that original height, which, on a horizontal plane, it never can. This thought experiment powerfully suggested that uniform motion does not, in fact, require a continuous external force, a revolutionary idea.
And Newton formalized this.
Yes, Newton built on Galileo's insights and formalized it into his first law of motion, often called the law of inertia. It states, quite elegantly, an object remains in a state of rest or of uniform motion in a straight line unless compelled to change that state by an applied external force. In simple terms, objects tend to keep doing what they're already doing. They resist changes to their state of motion.
So inertia is this resistance. Can you give us some everyday examples? The kind that might pop up in exam questions to test understanding?
Absolutely. Inertia is everywhere. Think about being in a moving car that brakes suddenly.
You lurch forward.
Right. Your body tends to continue moving forward due to its inertia. That's exactly why safety belts are crucial. They apply that necessary external force to stop you safely. Or, the opposite, standing in a bus that suddenly starts moving, you tend to fall backward.
Because your body wants to stay at rest.
Exactly. Your body resists being accelerated from rest. Even taking a sharp turn in a car, you feel thrown sideways. That's your body trying to continue moving in a straight line due to inertia while the car turns. For exams, classic demonstrations are useful. Striking the bottom coin from a stack of carom coins, what happens?
Only the bottom one shoots out, the rest drop down.
Because the inertia of the upper coins keeps them momentarily at rest, resisting the sudden horizontal force. Another one. Place a coin on a card over a tumbler. Flick the card quickly.
The card flies off, the coin drops into the tumbler.
Again, the coin's inertia keeps it in place vertically while the card is removed horizontally. Even spilling water from a tray, if you turn too quickly, the water tries to keep going straight due to inertia.
These examples really drive it home. Now, does everything have the same amount of inertia, or does it vary?
That's a key point. No, not all objects have the same inertia. It's much easier to push an empty box than a full one, correct?
Definitely.
Or easier to kick a football than a heavy stone of the same size. This leads directly to a fundamental concept you absolutely need for exams. The mass of an object is the quantitative measure of its inertia. More massive objects have more inertia. They offer greater resistance to any change in their state of motion or rest. Mass essentially tells you how stubborn an object is about changing its motion.
And Galileo, the man behind these initial insights.
Ah, yes, Galileo Galilei, born 1564. A truly brilliant mind. Not just a physicist, but also a remarkable craftsman. His contributions went beyond motion. His telescope observations provided strong evidence for the heliocentric model, challenging the Earth-centered view. He even designed the first pendulum clock. His relentless questioning of established beliefs really paved the way for Newton. A pivotal figure.
Okay, so the first law tells us that an unbalanced force causes a change. But the second law tells us how that change happens, right? And how to measure the force itself. What factors determine, say, the impact of a moving object.
Exactly. The second law gets quantitative. Think about impact. What's the difference between being hit by a table tennis ball versus a fast-moving cricket ball?
Big difference. The cricket ball hurts a lot more.
Right. Or consider a stationary truck versus the same truck moving at speed. The moving truck has a huge impact potential. These observations suggest that the quantity of motion, or the impact an object has, depends on two things: its mass and its velocity. Newton introduced a crucial concept to capture this: momentum, usually denoted by p. Momentum is defined simply as the product of an object's mass and its velocity v. So the formula is p equals mv, very important for exams. Momentum is a vector quantity. It has both magnitude and direction, and its direction is the same as the object's velocity. The SI unit follows from the definition. Mass kg times velocity, so it's kilogram meter per second, kilogram to kilojoule.
Okay, P equals mv. How does this relate to force and the second law?
Well, since an unbalanced force is what changes an object's velocity, it must also change its momentum because momentum depends on velocity. Newton realized that the rate at which this momentum changes is key. How quickly does the momentum change? This rate of change depends not just on how big the force is, but also on the time over which the force acts. Think about pushing a stalled car. A quick shove might not do much, but a sustained push over time gets it moving. So Newton's second law states more formally: the rate of change of momentum of an object is directly proportional to the applied unbalanced force and takes place in the direction of the force.
And the famous F mean, where does that come from?
Ugh, the cornerstone equation. EFMA is the mathematical consequence of that statement about the rate of change of momentum, assuming the mass of the object remains constant, which is true in most everyday situations you'll encounter. If F is the applied unbalanced force, m is the mass, and a is the resulting acceleration, then the relationship is F equals ma. This is incredibly powerful. It gives us a way to calculate force. The SI unit of force is named after Newton himself, the Newton N. How is 1 Newton defined? It's the force required to give a mass of 1 kilogram and acceleration of 1 meter per second squared, 1 meters F. So 1 N equals 1 kilogram SF. This formula, EFMA, is central to solving so many physics problems.
Absolutely foundational. Can you walk us through some practical, real-world applications of this second law, things our listeners might observe or need to analyze?
Certainly. The second law is visible everywhere. Take cricket again, a fielder catching a fast-moving ball. What do they do with their hands?
They pull them back as they catch the ball.
Exactly. Why? By pulling their hands back, they increase the time over which the ball's momentum changes from its initial value to 0. Now, the change in momentum is fixed. The ball has to stop. But the force experienced is F equals EP. By increasing the time, they decrease the rate of change of momentum, and therefore they significantly reduce the impact force F on their hands. It prevents injury.
Makes sense. Increase time, decrease force for the same momentum change.
Precisely. High jumpers landing on thick cushions or sand pits. Same principle. The soft landing increases the time it takes for their body's momentum to become 0 upon impact, reducing the force they experience. Or think about a karate expert breaking a slab of ice or tiles. They strike very quickly. They apply a very large force over an extremely short time interval. This causes a massive rapid change in momentum, enough to exceed the breaking strength of the material.
So controlling the time of impact is key in many situations.
Absolutely. And one more interesting point, conceptually important, you can actually derive Newton's first law from the second law. Look at F mass May. If the net external force F acting on an object is 0, what must the acceleration A be?
0.
Right, and what does 0 acceleration mean? It means that the velocity isn't changing. The final velocity v is equal to the initial velocity u. So, if the object was initially at rest, u remains at rest, v 0. If it was moving with a uniform velocity, ua 0, it continues to move with that same uniform velocity, which is exactly what the first law states. It shows the internal consistency of Newton's framework.
That's a neat connection. Now, for our listeners focused on exams, applying FI in numerical problems is critical. Could you maybe walk through 1 or 2 typical examples focusing on the steps?
Let's do that. Take example 8.1 from the source. It gives a constant force acting on an object and asks about acceleration and final velocity. Let's say a force of 10N acts on a 5 kilogram mass, initially moving at 3 meters. This force acts for 2 seconds. We want to find the final velocity. First step, find acceleration using ESMA, rearranging O5 FM. So N and 5 kilograms equals 2 meters force.
Okay, acceleration is 2 meters per second squared.
Second step, use a kinematic equation to find the final velocity. We know initial velocity u is 3 meters, acceleration a equals 2 meters seconds, and time t to 2s. The relevant equation is v equals an e plus at. So v equals 3 meters plus 2 meters south 2s equals 3 meters plus 4 meters equals 7 meters.
So the final velocity after 2 seconds is 7 meters.
Correct. The problem might then ask, what if the same force, 10N, acts for 5 seconds instead? The acceleration is still the same at plus 2 meters of sevs. But now t is breaking it down. Identify knowns, identify unknowns, choose the right formula, FMAC kinematic equations, and calculate step by step.
That structured approach is vital. What about a problem involving braking, like example 8.3?
Braking problems are common. Example 8.3 describes a car of mass of 1,000 kilograms moving at 108 kilobarids that stops in 4 seconds. We need the braking force. First crucial step, unit conversion. Velocity must be in MEs. 108 kilometers is 108, 30 meters, 26 hundredths equals 30 meters. This is the initial velocity. The car stops, so final velocity v is 0 meters. Time t is 4s, and mass m is 1,000 kilograms. Step 1, find acceleration. Use a VOP of UTA, 0 meters, 4 meters similar, and a SN of 7.5 meters similar.
The negative sign indicating deceleration.
Exactly. Retardation or deceleration. The acceleration is opposite to the initial velocity. Step 2. Find the force using F acerma. F is 1,000 kilograms, net is 7.5 meters acerma, or net is 7,500 N.
Again, negative force.
Yes. The negative sign confirms the force opposes the motion. It's the braking force. Paying attention to signs is very important in these problems. Other examples in the source cover comparing forces. Example 8.2, combined masses. Example 8.4, and using graphs. Example 8.5. But the core logic always revolves around F and related kinematic equations.
Those detailed walkthroughs are incredibly helpful, thank you. So we've covered how forces affect single objects. But interactions usually involve at least 2 objects. What happens then? This must bring us to Newton's third law.
Indeed it does. Newton's third law deals specifically with interactions between two objects. It's famously stated as, to every action there is always opposed and equal reaction. Or, perhaps more clearly for understanding, when one object exerts a force on another object, the second object instantaneously exerts a force back on the first. These two forces are always equal in magnitude and opposite in direction. Now, here's the absolute critical point to remember for your exams, a common point of confusion. These action and reaction forces always act on two different objects. They never act on the same object, so they never cancel each other out in terms of the motion of a single object.
That distinction, acting on different objects, seems crucial. Can you illustrate this with some clear examples?
Certainly. Let's revisit kicking a football. Your foot exerts a force on the ball. Let's call this the action. Simultaneously, the ball exerts an equal force back on your foot, the reaction. The force acts on the ball, causing it to accelerate, and the reaction force acts on your foot, which you feel.
So two forces, two objects.
Exactly. Another good demonstration, connect two spring balances, A and B, end to end. Pull on balance A. Balance A exerts a force on B. You'll see that balance B reads that force. But balance B also pulls back on A with an equal force, and balance A shows the same reading. Equal and opposite forces on two different balances. Think about walking. You push the ground backward with your foot, action. The ground, in turn, pushes you forward with an equal and opposite force reaction. It's the ground's reaction force that actually propels you forward.
That makes sense. The force on you moves you.
Precisely. Firing a gun, the gun exerts a strong forward force on the bullet, action. The bullet exerts an equal and opposite force back on the gun, reaction. This reaction force is what causes the gun to recoil. Or a sailor jumping from a small boat onto a dock. The sailor pushes off the boat, action, force on the boat. The boat pushes back on the sailor, reaction, force on the sailor, propelling them forward, but the action force on the boat pushes the boat backward, away from the dock.
Those are very clear examples. But here's a question that often comes up. If the action and reaction forces are always equal in magnitude, why don't they always produce the same effect? Like, the gun recoils, but the bullet flies off much faster.
That is an excellent and very important question. It highlights a crucial nuance. The forces are equal in magnitude, yes. But remember Newton's second law, F equals ma. The acceleration produced by a force depends not only on the force, but also on the mass of the object the force is acting upon, A equals Fm. In the gun and bullet example, the action force on the bullet and the reaction force on the gun have the same magnitude, F. However, the bullet has a very small mass, while the gun has a much larger mass pen. So the bullet's acceleration, a bullet equals ang bullet, will be very large. The gun's acceleration, a gun, will be much smaller because its mass is larger.
So equal force, but different masses lead to vastly different accelerations.
Exactly. The effect's accelerations are different because the masses on which the equal forces act are different. This is key to understanding why recoil is noticeable but manageable, while the bullet achieves high speed. The same principle applies to the sailor, and the boat moves back, but likely with less acceleration than the sailor jumping forward, depending on their relative masses.
Okay, that clarifies the third law significantly. So, wrapping up our journey today, we've navigated the core ideas of force itself, distinguished balanced from unbalanced forces, and then explored Newton's three foundational laws. The first law of inertia, the second law quantifying force as F and relating it to momentum change, and finally the third law of action-reaction pairs.
That's a good summary. And the key takeaway for everyone listening, especially for your exams, is not just memorizing the laws. It's about understanding the concepts behind them and being able to apply them. Remember, inertia is resistance to change. Mass measures inertia. An unbalanced force causes acceleration, changing velocity and momentum. And every interaction involves pairs of forces, equal and opposite, acting on different objects.
We strongly encourage you to revisit the numerical examples we discussed and tackle similar problems in your textbooks or practice materials. Physics really solidifies through application. Stay tuned for more deep dives designed to give you exam-ready insights into complex topics. In this deep dive, we cover the following topics: Introduction to force and motion, balanced and unbalanced forces, Newton's first law of motion, the law of inertia, inertia and mass, Newton's second law of motion, momentum, SMA, and numerical applications, Newton's third law of motion, action-reaction pairs.
Follow us for more such content and subscribe so you never miss a topic.